So good morning, ladies and gentlemen. Today's morning lecture will be given by Andrzej Pigulski from the Astronomiczny Uniwersytet of Wrocław, who will speak about the BRITE mission. So Andrzej, please.
Thank you, Marek. Good morning, everyone. I would like to thank Marek for inviting me to give a talk on the BRITE mission, which is the mission I'm involved in for already 10 years, which is a long time. So I hope that I will give you a good overview of the mission, which the data from this mission, I suppose, can be used as a complementary source of data for your scientific work. So I will make also some brief comparison with TESS, also Kepler. So let me start this mission. Let me start the presentation and the short introduction of the mission itself. BRITE comes from a BRITE Target Explorer, and the nanosatellites, the satellites are fall in the category of nanosatellites, which means the satellites of the size like this one, which is a cube with a side of 20 centimeters long. So this is a really very small satellite. You can easily carry it. Its mass is about 7 kilograms, and it hosts a telescope which has only 3 centimeters in diameter, equipped with the uncooled CCD. So this is not an equipment you would probably use when doing ground-based work, but this was I think, a very interesting exercise, and the challenge at the same time to see if such a small thing can be used to do useful scientific photometry from space. So the project, in fact, the father of the project, one of the fathers was Sławek Gruczyński, who already in the 1970s and 1980s considered which kind of satellites can be launched by Canada, because Sławek Gruczyński is the emeritus professor in the University of Toronto. He emigrated from Poland during the martial law and settled in Toronto. He was the chair of the David Download Observatory for many years, and also one of the fathers of the Canadian satellites doing astronomy from space. So the first Canadian satellites with scientific satellite was most satellite you probably know. So BRITE in some sense was the next one, which is of course smaller than most. But the idea was to study the variability, to do photometry, and study variability of bright luminous stars from space. Well, nobody else tried this kind of observations before launching BRITE, so we expected that there could be some surprises and some unexpected effects we didn't predict. So at the beginning, two countries, Austria and Canada, were involved in the project. This was the same countries which worked with most satellite. And this was idea by Sławek Gruczyński to involve also Poland in this project. Fortunately, we quite easily got money to build the two satellites. So at the end, the 6 nanosatellites of this kind were built, and 3 of them were equipped with the red filter, the 3 other in the blue filter. Because the idea was also not to get the photometry, but to get 2-color photometry, which can be helpful in many scientific purposes, including, for example, mode identification in pulsating stars. So the 6 satellites were launched in 2013 and 2014, And as you can see, they are in space for already at least 6 years. One of the satellites, Bright Montrand Blue Filter satellite, didn't detach from the launcher, so it didn't work at all. This happens in this business. And another one, Austrian Unibright, failed after more than 6 years of observations. This is still much longer than the nominal time of work which was predicted. It was 2 years only. So all these satellites work more than 3 years longer than predicted. The two bright filters, the two bright passbands, blue and red, marked with B and R, are shown in this plot in the at the bottom of this slide. As you can see, the blue filter is about 420 nanometers. The red filter is centered more or less on the 620 nanometers. Why we want to observe bright stars? Well, in general, the photometry of bright stars is very difficult from the ground. So, of course, spectroscopy is easy. So usually bright stars have very good spectroscopy, have a lot of other kinds of observations, for example, interferometric observations and polarimetric observations and some other things, but photometry is really very difficult. The main purpose, the main motivation for this mission was to get precise as much as possible with this small thing, photometry for the bright stars. Of course, nanosatellite is also the advantage of launching scientific nanosatellites is because this satellite is really it's affordable, but well, it's a single institution. For example, one of BRITE's was built by the University of Vienna, so a single university can afford building such a satellite. And of course, some new techniques could be tested. For example, because the mass is very low, it's really difficult to stabilize in the satellite and aim the telescope on the desired position. So this was also a test for some technical parts of the satellites, trackers, the systems of fine pointings, and some other things. Well, this is the comparison of the size of BRITE and Kepler. Of course, money for BRITE is well also much smaller than the cost of the Kepler satellite. What BRITE could observe? So at the beginning, we expected that the magnitude limit for BRITE satellites will be about 4th magnitude. There are about 500 stars in the sky which are brighter than 4th magnitude. So this was the number at the beginning. Of course, we knew that possibly fainter stars also could be observed, and some useful photometry can be obtained as well. You will see how this looks now. So this is more or less the bright sky, and brights could be aimed at any place in the skies, which is also very useful because we can choose the most important, well, the most interesting targets in the sky and aim the telescope there. The field of view of a single bright telescope is something like this, because the detectors are square, as you can see. And the diameter of the field of view is about 25 degrees, but in fact, in the direction perpendicular to this line is about 20 degrees, and it's not square and not rectangle. It's something like this. So there is some vignetting in the field. So not the whole chip is in fact used for photometry. And from this field, we choose targets which are most interesting and usually bright. And what is downloaded from the satellites to the ground are small parts of the system, the images around these fields. Usually this is the, let's say 20, 30 pixels wide subrasters, as we call them. The images are intentionally defocused. This is to allow longer exposure times and not saturate the detector. So this is the technique which sometimes is also used in other satellites to defocus the images. This was, for example, in Korea also used this kind of observations. So this is the first field which was observed by BRITE, the Orion field, because the observing strategy is to observe different fields in the sky. Usually a single field is observed for, let's say, half a year. Sometimes slightly shorter, but usually 5-6 months is a typical length of a BRITE run. Of course, because we had 5 working satellites, these satellites can observe different fields, and we usually observe it this way, which means that, let's say, 2 satellites observed one field, 3 satellites observed other field, or some other combinations were also used. So sometimes even 3 fields at the same time were observed by BRITE satellites. Usually we tried to get both the blue and red filter photometry for a given field, but this was not always the case. For example, during the last observations, we usually sometimes only red filter satellites observe a given field, and it makes longer exposure, which means that slightly fainter stars are observed. So as you can see, this defocusing makes the stellar profiles very weird sometimes. This is the first field, 15 stars in the Orion field, 2 satellites, Austrian, bright Austria blue filter, and Unibright UBR, the red filter satellites. The shapes are very different. So you can imagine that the photometry for such fields will not be easy. And of course, because we started observation in 2013 up to now, so over these 6 years, many fields were observed. These are the first 15 fields observed. You can see which satellites observed which field, how many stars were observed, how long the observations. So 170, let's say, or 160 days. That's the typical length of the run. So up to now, we observed over 50 fields, but many of these fields are re-observed. So which means that for some fields, we have 6 or even 7 runs of BRITE observation. This is very useful because, for example, if you look for periodic signals, the resolution is the better resolution. You get the better resolution, the longer observations are. And of course, you can detect smaller signals. These are the first 20 fields observed by BRITE. So this is the whole sky in the galactic coordinates. The curved line is the celestial equator. So we focus mostly on the southern hemisphere, just because in the southern hemisphere we have a large number of bright stars, especially the gold belt is covered by our observations. We have very small number of fields outside the galactic plane, just because our trackers also need bright stars. And we tried several fields outside the galactic plane, but our trackers failed to get fine pointing just because they didn't have enough bright stars. So this is another plot showing how the data are distributed in time and how different fields were by different satellites, different colors were in different satellites were covered. As you can see, for example, the Orion field, which is at the top of the plot, was reobserved practically each season by different satellites. So This is a typical procedure now. So now we usually re-observe fields just because we don't have interesting targets outside this field which was already observed, or we just cannot aim the telescope at the field outside the galactic plane for the reasons I have explained. The longest run we had was on the Vela Picture 2 field, which lasted 229 days. That was because Beta Pictoris, which is one of the targets in this field, was expected to underwent through so-called Hill sphere eclipse, which didn't happen, but Beta Pictoris is interesting for other reasons. So these observations are very useful. Which magnitudes have stars which we have already observed? So this is the histogram showing this. As you can see, the median magnitude of stars which were observed by BRITE is about 4.5 magnitudes, which means that in general we could observe much fainter stars than we predicted at the beginning, which is very good because if we can reach fainter stars, we can observe many more interesting targets in the sky. So the brightest star observed was Canopus. The faintest star we observed was about 8 magnitude. Well, there's one exception, but I'll show a small digression about this, what brights, which stars BRITE can observe. This is Eta Carina. This is not bright light curve. This is the photometry of Eta Carina over 200 years. This is very well-known object, also a binary. Everybody knows this homunculus nebula. The star is classified as luminous blue variable, and its brightness is the star is getting brighter and brighter, and we have already 4 seasons of observations of the star by BRITE. These are the first 2 seasons, and as you can see, there is some variability clearly in this plot. But once this variability is subtracted and the frequency spectrum is done, we have seen something like this. So you can see this is frequency spectrum of the residuals from this long-term variability. As you can see, there is a clear peak at the frequency about 1.3 cycles per day, and it's 2 harmonics. So once the phase diagram was made with this frequency, we saw something like this, which is clearly an eclipsing binary, which was a big surprise because, of course, Eta Carina is not known to be such an eclipsing binary, especially with this period, which is slightly longer than 1 day, 1.5 days. There's nothing like this in Eta Carina. And this thing was explained easily because there is an eclipsing star close to Eta Carina, about 1 arcmanic from Eta Carina, and of course because of this defocusing of images and the scale, which is about 27 arc seconds per pixel for BRITE data. Just this much fainter stars contributed to the light of the measured light of Eta Carina. So we saw this in the light cave. So this is a good example of a contamination which can happen not only in BRITE but also in other missions, also Kepler and TESS, if you cannot resolve spatial stars which are close to each other. So what is interesting, this star is about 10th magnitude. So because we could derive times of minimum light for the eclipses from the BRITE data for this star. So the message I would like to send is that BRITEs can provide scientifically useful information even for a star which is 10th magnitude star. This was not expected, of course. The contribution of this star to the light of Eta Carina is about 0.5% only. Okay, so that's the end of digression. Going back to the stars which were observed by BRITE. So this histogram shows how they are distributed with the spectral type. So it's well, because we choose stars which we want to observe. So of course, this is not just the same distribution as in the sky among bright stars. And as you can see, the histogram peaks at the early type stars, because indeed there were many projects proposed to observe early O, B, and A type star, also for Freya stars. With bright, there are many such bright stars of these types. And so the project, we can say that the project focuses on O and B type stars. So 53% of all stars observed by BRITE are O, B, and A type stars. O and B, sorry, not A. O and B type stars. And BRITE observed about 70% of all O and B type stars brighter than 4th magnitude. So if you want to do some science with O and B stars, and especially with the bright stars, you can be sure that BRITE observed such a star. A small summary of the, sorry for this Polish title, I overlooked this. This is a summary of observations. So up to now, we observed about 660 stars, 45 fields. This is not updated, so over 50 fields. On average, we observe 26 stars per field. Sometimes it's even more. For example, there was one field when we observed 51 stars. On the typical length of run is 5-6 months. The median magnitude, as I said, so the total number of single measurements about 70 millions. And the precision, which is of course an important part, is better than 1 millimeg per orbit for stars brighter than 4th magnitude. As far as the level of the detection level of periodic variability is concerned, we can measure signals with amplitudes higher than 0.1 or 0.2 millimeg. This is, of course, much more than Kepler or TESS can give us, but the advantage of bright observations is much better resolution, because the length of observations is, as I said, half a year, or for many stars, several years now. So the general conclusions from this is that the bright data meet expectations. So the project can be regarded as a success, not only because of the large number of observed stars, but also the precision of the photometry. This is not, okay, another diagram showing this is not updated, so we have now more stars than shown here. How the stars are distributed, I just want to say that most of the stars we observe is the upper main sequence, so O and B type stars, but also there are quite a large number of red giants and stars with smaller masses as well, A and F stars, for example. Okay, so now a few words about the problems we got with doing photometry with this star. So at the beginning, with the observations were made in the so-called stare mode, which means that the satellite was aimed at the given field, subarrested were selected, and simple aperture photometry was done with the rasters. As you can see, in addition to the images of stars, you can see hot pixels. Well, their occurrence was not a surprise, because this is uncooled CCD. Simply, this such a small satellite cannot host cooling equipment, so these are not cooled. Their temperatures range between 0 Celsius and 40 degrees plus 40 degrees Celsius, which is, well, quite unusual for CCD detectors to work. So the effect is the large number of hot pixels, and as was and at the beginning of observations, these were the first satellites were the Austrian BRITEs, which were launched. So we saw that the number of hot pixels increases very fast at the beginning of observations. We didn't expect this. Well, it occurred that the protons from the cosmic ray protons hit the detector and make some defects in the detector. This was not expected because, well, this is not the first to in space, but in general, larger satellites, more massive satellites, the CC detectors are shielded by all the systems of this satellite, which are there are many different things which shield the protons. This is not the case in BRITE because it's a small satellite. So once we saw this effect, this increasing number of hot pixels, which of course spoil the photometry, we tried to mitigate this. And one of the things which was changed was to change the observing mode. So the so-called chopping mode was introduced. What is chopping mode? So the raster which is selected is not square but rectangle, and at the, let's say, first image, the star is centered in the upper part of this of the subraster. Then the satellite is slightly moved to move the star in the lower part of the raster. This is the second image. Which then the third image is again made in the same way as the first image. So the star is again centered in the upper part of the raster, and so on. So there's and why this kind of observing? Just because the two consecutive images can be subtracted, and in the difference image, as you can see here, almost all hot pixels are gone, which means that with this difference image photometry, which can be obtained with this difference image, will be much better and not affected by these hot pixels. Well, this is not so well seen in the upper image, but in the lower image, when the star is much fainter, you can see that the star itself is barely seen in the original images. Only after subtracting the images, you can easily see the profiles of the star. So the chopping mode of observing was one of the ways to mitigate the detector defects. As you can see, some other examples of stars and differential images which are used for photometry are shown here. The other way was to introduce some shields around detectors, because when we first spotted these defects, still 3 BRITE satellites were on ground, not launched. So the Canadian satellites, where there was a shield of tungsten put behind the CCD detector of the Canadian satellites. In the Polish satellite Heveliusz BHR, it was the Boratron shield, 10 millimeters thick, just because there was more room behind the CCD detector in this satellite. Heveliusz has slightly different optics. It has only 4 lenses. The other satellites have 5 lenses. This really helped. As you can see on the plots on the right-hand side, the dark-kind growth rate is about 2 times smaller in the Heveliusz than in the unshielded satellites. These two things, I mean, the chopping mode, the introducing of chopping mode of observing, it was introduced in at the beginning of 2015. And this shielding in some satellites Both these things, let's say, extended the mission and extended the time when useful photometry can be obtained with bright satellites. Otherwise, we probably would have to finish our observation earlier than well, the mission would be probably already ended. Of course, this is not only because the photometry made with such images when you have very weird stellar profiles, and of course stability of the satellites is not perfect, so usually the images are smeared, and of course because temperature of the optics and CCD changes, the profiles change with the temperature. An example is shown here on the when you have the two profiles of the same star at temperature 15 and 35 Celsius. They are different, as you can see. This makes photometry very difficult, and of course, this original aperture photometry uh, cannot be directly used for scientific purposes. So we have a pipeline for removing instrumental effects which are in this photometry. This is done by decorrelation, one-dimensional and two-dimensional decorrelation. For example, here you can see the raw magnitudes plotted against two parameters. The PSFC parameters is a parameter which is a measure of smearing of the profile. The other parameter is just the location of the center of the profile in the raster. This color plot at the bottom of the image is two-dimensional correlation between position of a star in a raster in two directions. Different colors show you how this depends, how this raw magnitude depends on this position. So this can be corrected quite effectively. As an example of what's the comparison of the raw data and the decorrelated data in shown here. Raw data is the blue points, the red points are the correlated data. So as you can see, we can quite effectively correct for all these effects. Okay, so it's time to go to the science, which is of course the most interesting thing we get with BRITE, and show you what we done with which science has been done with the BRITE data, what can be done. This science was presented at the BRITE Science Conference. The first was in Poland in 2015. Second in Austria in 2016, the third in Canada in 2017. The last conference was when BRITE was, in fact, the fifth anniversary of BRITE constellation was celebrated, was the Vienna conference 1 year ago. Stars and the variability observed from space, when, of course, this is not only the BRITE science conference, but many other space observatories. The data from space observatories were presented there. So because it was the birthday party, it was the fifth anniversary, you can see here, and there was some celebration. Party is a party. You probably know some persons in this picture. Okay. Some summary of scientific results. So by now we published over 200 papers which are related to BRITE mission. This includes 35 refereed papers. These are the most important papers. Some of them, some result, I will present you some examples of the science which was done with this, which BRITE data. We have 3 technical papers which describe the mission, describe the photometry and all these things. We have many conference papers showing smaller scientific results and also other things, the reductions, the problems also with the BRITE data. We have some 47 papers from supporting programs. These are programs which were aimed at, let's say, ground-based support observation for bright targets, or some surveys like polarimetric survey of bright stars with the purpose to use these observations together with bright data. Some technical papers and of course outreach papers as well. As far as outreach is concerned, so you can see that brights can be done not only with with the, well, there are some models of brights with a gingerbread or with Lego. So there are some members of the team like this shape very much, as you can see. Okay, let's go to the science. So the first example is what we do for very massive stars, because as I said, the project is focused mainly on massive stars, luminous stars. Which means in particular Wolf-Rayet stars and O-type stars. So what is interesting in this star is, of course, the origin of variability, because what we measure with photometry is the variability. This can be done with the origin can be pulsations, spots, of course, stellar winds, clamps in stellar winds, for example. Of course, many of these stars are in binaries, which is also very interesting. And we have quite a large sample of Wolf-Rayet and O-type stars in bright observations. We observed also Eta Carina, as I showed. This is the very bright and very interesting LBV star. So there are several papers, 8 papers published on these massive stars, and of course there's still a lot of data which can be published. Well, I showed that we have published 35 scientific papers with bright data. I think that we can easily double this number with this data, with the data we already have. Okay, so going to these, in one of these papers, which was phased out over Tahina Ramanantsa, we dealt with the possibly most massive star observed by BRITE, which is Zetta Puppis. These are the bright blue and red filter observations covering about half a year. The variability can be easily seen in this data. And here is the frequency spectrum of the data of blue and red filter data. On the left-hand side, you can see that the spectrum in the range between 0 and 7 cycles per day. And you can easily spot the 2 peaks, which the first peak at the lower frequency is the rotational frequency of the star, which was in fact different than could be found in the literature prior to bright observations. The other peak is the harmonic, which means that the variability is not sinusoidal, which can be seen in the middle panels. The shape of the light curve is quite similar in blue and red, because just these observations are correlated, as you can see in the right-hand plot. Well, this rotational variability is not the only variability in this star. As you can see in the frequency spectrum, the power in the spectrum increases towards lower frequencies. This is not noise. This is the real variability of the star. However, this is stochastic variability, which means that no single periodic frequencies can be indicated. This rotational variability is also not stable in time either. So this time frequency diagram on the left-hand side shows how the amplitude of the main peak, which is the rotational frequency, and its harmonic changes with time. And as you can see, there are epochs when the harmonic is stronger than the than the main frequency, which means that the shape of the rotational light curve changes with time. And on the right-hand side, you can see the shapes of the mean rotational light curve, but also the shapes of the light curve at 5 different time intervals covered by BRITE. The rotational period anyway is equal to 1.78 days. What was important, that this photometry could be used to recover the location of bright spots at the surface of the star. And as you can see, because this shape changes, this means that the location and intensity of this bright spot changes also with time. That was very interesting. This is another plot showing frequency spectrum or time frequency diagram. This is, in fact, wavelet transfer of blue and red data, showing how this behaves with time, but not the rotational frequency, but this stochastic variability. And another plot which shows also the spectra, because spectral observations were also obtained. And in the profile at the top, you can see the profile of the helium line, which is an emission, but this line also changes with time, and the residual changes with respect to the mean profile can be seen in this gray plots. There are gaps in time, of course, in the spectroscopic observations. What is important is the plot on the right-hand side showing that the integrated residual intensity in this helium line is correlated with the photometric variability in BRITE, which means that the variability which is seen in the line is related to the variability which is seen, this stochastic variability which is seen in the light curve, which means that the variability, because the line is the line comes mainly from the outer atmosphere of the star when the stellar wind dominates. This means that stellar wind has its origin already in the lower photosphere when from the photosphere when the photometric signal comes from. This was very important. So this is the artist model of this star, showing that there are two main bright spots, and as the star rotates, we can see this variability with rotational velocity, but also the clumps in the stellar wind, which also cause the stochastic variability. So the general conclusion from this, so the first time when it was shown that there is a correlated spectroscopic and photometric variability in such a massive and hot star. And there are two so-called rotating interaction regions per rotation period, at least in this star, but also in other stars, similar things can be seen. I mean, O-type stars. Okay, the next topic is, of course, pulsations, because in general, in the sample we observe it, we have about 300 stars which fall in Beta Cephei and SPB instability strips. These are stars, let's say, with masses over 2.5 solar masses. So we expect to see many pressure or acoustic modes. These stars are called Beta Cephei stars, and many G modes, gravity modes. These stars are called G modes. Of course, there's a large area in this diagram when the two instability strips overlap, which means that we can expect hybrid stars. I mean, stars which show both G and P modes. Not so many such stars were known before BRITEs were launched. So we expected to detect many more. Let me show you just a few examples. Beta Centauri, one of the brightest stars in the sky, or Agena, which is also a binary, spectroscopic binary. This is the radial velocity curve on the right-hand side, eccentric binary. But because the star is quite close to us, there is also an interferometric orbit, visual orbit of the two stars. Which allows to derive masses with quite a good precision of about 1%, as you can see. So we know exactly which are the masses of the components, which helps very much in the seismic modeling of the stars, because as you will see, the star is pulsating. So the pulsations were known from, it was known that the pulsations are excited in the star, but this is the stellar profiles. One star is rotating slowly, the other one, the AA component, is rotating much faster. The ground-based observations, mainly with the spectroscopy, show two frequencies, but usually, as you can see, it was in fact not known which frequency is the true one, just because the aliasing, the ground-based observations, are affected by strong daily aliasing. So sometimes the daily alias was identified as the true frequency. We now know this just because we have these bright observations. There was no detection of variability practically from photometry. So there was no good photometry at all for Beta Centauri. So with BRITE, what we get with BRITE data, these are frequency spectra. At the top, this is the original frequency spectrum. As you can see, the highest modes have amplitudes below 2 millimax, which this is quite small. But in total, we detected 19 periodic terms, which include 8 G modes, 9 P modes in two combinations. And it's clear that this is the hybrid Beta Cephei SPB star. Of course, we have two components there, so it is quite possible because the other components is less massive. So we in fact don't know which mode is excited in which star. Both stars are in the Beta Cephei and SPB instability strips. So this is the problem which has to be resolved when the star is modeled. The other example is Sigma Scorpio, the star which was known to be a Beta Cephei star with these 4 modes marked here with the red triangles. So these are the frequencies which were known from earlier observations. However, the amplitudes in bright observations are about 5 times smaller than were in the past. So this means that this star changes amplitudes very fast. In addition to these 4 modes, we detected 6 new modes in the star, including 3 G modes, which is very important because this also makes Sigma Scorpio another hybrid Beta Cephei SPB star. This hybridity is important in modeling just because P modes probe the external part of the star, while G modes usually provide an information on the core, on the areas of the star closer to the core. So in fact, we have these frequencies carry an information on the whole interior of the star. And another star, Theta Ophiuchi, which was also known to be a Beta Cephei star, so P modes were known. With BRITE data, we discovered, I don't remember how many, but about a dozen or so G modes in this star, and also in not known P mode, one P mode, which was not known earlier, which completed the rotational split multiplet, which is also important. So these are just few examples because we have many more such stars. So we have about 20 hybrid stars with large number of modes, which means in this case 10, sometimes even 20 modes. And these stars have different rotational variabilities, which means that this is a very good sample for astroseismology. So the general conclusion is that hybridity is very common among B-type stars, which we now also know after TESS observations were launched. We also have many stars that show hybridity. So this gives us the key information for revision of opacities, because modeling is not always successful, and we see that there is a need for changing opacity, stellar opacities, and studies of these stars can provide the key for the clue for these changes. We can, of course, study the internal rotation of the stars and the extent of convective overshooting from the core, which is important, for example, for modeling these massive stars and their evolution, because these stars become supernovae later on. Next important discovery with BRITE is the discovery of so-called heartbeat stars and massive heartbeat stars. Heartbeat stars were discovered by Kepler, although there were some observations before Kepler that showed this phenomenon. These are eccentric binaries with high eccentricity in general, and during the periastron passage, the stars are deformed in the way that this results in so-called heartbeat close to the periastron passage. But Kepler stars, practically all Kepler stars, are low mass heartbeats. This star, the Iota Orionis, was the first massive star that showed with a heartbeat. As you can see, the masses of the components are 23 and 13 solar masses. And this is this plot shows not only the heartbeat in the blue and the red light curve of BRITE, but also the radial velocity curve, clearly showing that we have an eccentric binary here. The primary is O-type star, the secondary is B1 type star. In addition to this heartbeat, what can be seen is the variability outside this heartbeat, short period of heartbeat. So we can clearly see some variability, which is in phase with the orbital phase. So it doesn't average. These are forced oscillations because the frequencies of these oscillations are the exact harmonics of the orbital frequency, quite high harmonics. In this case, as you can see, there are 6 detected. One is uncertain, but the other 5 are quite certain, special dose between 25 and 33 orbital frequency. Especially at the lower part of the lower plot, because these are the frequency spectra for different bright data. There are 2 seasons of Orion observations in red and blue. This was not the only heartbeat star detected with bright data. Another one is Tau Libre, which the light curve from blue or red data of BRITE is phased with the orbital phase can be seen. And the lower plot, the upper plot, shows the frequency spectra with the number of harmonics. As you can see, this is again we see again the heartbeat, but also close to phase 0, one can see something which looks like a very, very shallow eclipse. Well, we couldn't be sure, but we looked for other data for this star, and there were data obtained by SME between 2003 and 2010. This is in fact, solar observatory, but stars were observed there as well. And as you can see in SME observation, the eclipse is much, much deeper. Why this eclipse depth changes? Just because we have something like the apsidal motion. And of course, at different phases, we can have deeper or shallower eclipse. So this is spectroscopy of this star, which was obtained. And here we have about two stars, also quite massive, although less massive than in Iota Orionis, 6.754.3 mass solar masses. And this is the full period of apsidal motion showing how the eclipses in this star will change with time. So the blue light curve is the light curve at the time of SME observations. The red light curve is the light curve of this star at the time of BRITE observations. Of course, this eclipse will cease, as you can see, in about 30 years from now. The secondary eclipse will occur in this star. So this is an interesting example of eclipsing of a star with a vanishing eclipse. The other heartbeat star detected is Eta Orionis, where here the orbital period is much longer, about 90 days, and you can clearly see an increase of brightness at around phase 0. We also have spectroscopy for this star, which clearly shows it's an eccentric binary. In this system, we have two stars, about 6 solar masses. So it's quite similar to Tau Libre. So with this observation, there's another star, Epsilon Lupi, which also shows the heartbeat. So we have 4 stars with BRITE data, at least 4, which showing massive systems which show heartbeat phenomenon. So a new possibility opens. We can investigate tidally excited oscillations of massive stars. And this is one of the very few, in addition to stay small, methods to probe stellar interiors, because such tidal effects can also tell us something about the interiors of the stars. Okay, another thing, with BRITE data, we discovered pulsations in a very close binaries. This is deltapictoris, again, a massive system, 16 and 9 solar masses, eclipsing. And as you can see, the magnitudes between eclipses are not constant, which means that the stars are distorted and the ellipsoidal effect is quite strong. And in addition to this variability due to eclipses, we could find pulsations with amplitude about 2 millimegs in bright red data, and also an orbital combination of this frequency, which means that the amplitude changes with orbital phase, which is very interesting. This could be much better traced with TESS data. Deltapictoris is in the continuous viewing zone of TESS, so there's about 1 year long run of TESS observations for deltapictoris, which allows, as you can see here, to show how the amplitude of this pulsation changes with the orbital phase. These changes are very interesting, not only amplitude, but also phase changes. And this is something which we are now trying to model. But anyway, this is one of the situations when we see that distortion of a star changes the shape of pulsations on its surface. And it's very interesting to test how this compares with the theory, which is not elaborated well yet. Okay, and at the end of my talk, because I'm talking almost an hour already, I would like to show you another very interesting case. So this was in 2018, BRITE observed a star field in Carina. This is Carina Nebula, as you probably know, can recognize. And one of the targets which was included in the list of targets observed by BRITE was this star, which is not arrowed, but this brighter star, which is close to the arrow. This is the K-type giant star, which was not very interesting from our point of view. But surprisingly, close to this star, a nova occurred. This nova is known as novacarina 2018 or V906 Carina. It was discovered by the SSN survey and designated also SSN 18FV. So this was a complete surprise. As you can, this is bright images of this K-type giant, HD 92063, on the left hand, and we started observation because the nova erupted. So when the nova erupted, the image of the star looked like this. On the right-hand side, you can see that there are two stellar images overlapping. The other stellar image comes from V906 Carina, this nova. So I have estimated the probability to serendipitously detect or see bursting nova when observing like BRITE observes. So the chance to get such observations and to erupt nova in the field of view of BRITE rasters, which are very small in comparison with the whole field, of course, the probability is 1 in a million. So this was really we were really very lucky to get this star. So this is the part of the light curve of the nova, which in itself is quite interesting. Two satellites observed it was BRITE Toronto and the BRITE values, the two images of the nova and the other star were better separated. So this is the full light curve of the nova from BRITE. As you can see, it covers about 150 days. The first part is by Toronto. The rest of the light curve is from Hevelius. This is the spectrum from SALT showing that this is indeed a nova, a very interesting nova. And what is important that the BRITE observations were were, as you can see, uninterrupted, which were very important and quite precise, which is very important in looking at different dependencies here to see how the optical observations is related to the variability of gamma rays here measured by the Fermi satellite. So as a result, it was, the most important result of the paper which has appeared in these observations is that it was told that the luminosity of the classical nova is powered usually mostly by the nuclear burning on the surface of a white dwarf after the initial runaway. Our observations showed that most of this energy comes from shocks which are internal to the nova ejecta, just because this multiple maxima come from different shocks, and we can see the same in optical and in gamma rays. So there is a paper in Nature Astronomy which is based mainly on the BRITE data. Okay, so this is the last slide of my presentation. So instead of conclusion, I would like to show you the BRITE Constellation Wiki page, which when you can find information on BRITE photometry. Also links to scientific papers, which we will publish, to all papers, BRITE papers, to public data archive of BRITE. We are now preparing also not only the raw data of BRITE, which can be downloaded by any user, but we plan to provide also the correlated data, which will be very useful for potential users of BRITE photometry, because these data were just ready for use. We have also a Facebook page if you would like to look there. All these links can be found in this BRITE wiki page. Thank you very much. If you have any questions, please go ahead.
Thank you, Andrzej, for a very nice talk. We now have very nice comparison with Kepler, TESS, and other missions. So please, are there questions, comments?
Thank you very much for interesting talk. Thank you. I have a technical question. And how data is transferred from BRITE satellite to Earth?
We have several ground stations. There is in each of the participating countries has a ground station. So there is a ground station in Toronto, in Warsaw, and in Graz. And well, there is simply a small antenna at each of the satellites, and then it's downloaded during the pass. So when the satellite can be seen by the antenna, the data are downloaded. Just because if I didn't say that, but the observations by satellites are not continuous. So the orbit is about 100 minutes. It takes about 100 minutes. It's slow orbit. So during these 100 minutes, only about 20 minutes is spent on observations. The other time is used for downloading data from other things, because not only simply the target is not visible during the part of the orbit, so the satellite cannot observe the field. But it's done in a usual transfer within the antenna. Of course, this transfer is not very fast, so we can't observe many more stars. Well, also because the exposure time, the typical exposure time for bright observation is about 1 second, and because we need to cover as long time interval as possible. So the observations are made in such a way that there is a 1 second exposure, and then the satellite waits for 20 seconds, because these are usual typical time interval between consecutive observations is 20 seconds. So the satellite waits 20 seconds to make the next observation. Of course, part of this time is spent on changing slightly the position of the satellite, because, as I said, we observe in this chopping mode, but still some time is simply lost. We could observe denser, but this would we couldn't transfer all the data to the Earth.
Thank you very much. Thank you.
This is also the reason why the whole images are not transferred to the ground. But Kepler did exactly the same. So the stars were chosen, for which photometry was chosen. Only some, from time to time, the full frame images from Kepler were downloaded to the Earth.
Okay, thank you. Any other question? Actually, I had one. I was wondering if there is a chance to get the data, and you answered it on your last slide.
Yes, there is a chance to get the data.
And
let me say a few words. Even if the data are not available, because now only raw data are available. Even if the data are not available and there is a star interesting for you, you can always contact the so-called contact PI and ask him or her whether he is interested in cooperation, or whether, because sometimes some data are simply not used. Somebody will be happy if you will get the data and do something with this.
Okay.
Of course, as I said, we will try to provide the correlated data, which can be directly downloaded and used for science.
And in this decorrelated data, will there still be a blending? I mean.
Yes, well, blending is in this contamination is unavoidable. So if you have some stars which are close to each other, let's say 1 arc minute, 2 arc minutes, you will get photometry of the whole clamp, so 2 stars or 3 stars.
Okay. Any other comment or question? If not, thank you very much, Andrzej, for your talk.
You're welcome.
And now we can proceed with the group work.